In the previous video, I introduced you to the idea of torque. Loosely speaking, we can say that the torque is the twist delivered to an object by a force. Another way of putting it is to say that the torque describes the effectiveness of a force in changing an object's rotational motion. There are a couple of ways of calculating the torque, so here I'm going to review the formula that I showed you in the previous video, and then we're going to practice using that formula on a couple of straightforward examples. Here's the idea. Let's say that we have an object here that can rotate. We start by identifying a center of rotation. In a practical situation, it's often, but not always, fairly obvious what we should take the center of rotation to be. So for example, if we are opening or closing a door, we would take the axis passing through the hinges as the center of rotation. If we're looking at the rotation of a bicycle wheel, we would probably take the axis passing through the axle of the bicycle wheel as the center of rotation. Anyways, here's the idea. Let's say that we have a force acting somewhere in the body of the object. What we do is we draw a position vector that goes from the center of rotation to the point where the force acts. The torque is then plus or minus the distance from the center of rotation to the point where the force acts, multiplied by the strength of the force, multiplied by the sine of the angle between the extension of the position vector and the force vector. The plus or minus here is to keep track of whether that particular torque is trying to make the object rotate clockwise or counterclockwise. Normally, we would take counterclockwise to be our positive direction. So then a torque which tries to rotate the object counterclockwise would count as positive, and a torque which tries to rotate the object clockwise would count as negative. Here we're just going to do a couple of sample calculations using that formula. You can see that I have defined counterclockwise to be the positive direction. I have this object here that can rotate, and I have set the center of rotation of the object right here in the center. And I have two different force vectors which are acting on the object. Over here I have force vector 1. So to get from the center of rotation to force vector 1, I draw a position vector that goes from the center of rotation out to force vector 1. The strength of force vector 1 is 5 newtons. The distance from the center of rotation to the point where force 1 acts is 20 centimeters. To understand this 30-degree angle here, notice that I have a right angle in here. So that 30-degree angle is between the direction of the force vector and this segment here, which is perpendicular to this position vector. So the first thing I'd like you to try and do is calculate the torque associated with force 1 using the formula over here. So maybe pause the video, give that a shot, and when you've given that a shot, rejoin the video. First, does the torque from force 1 tend to make the wheel rotate clockwise or counterclockwise? To show that, I have this circular piece of paper I cut out, so I'm going to come to that equivalent point and exert a force in the direction of F1. And you can see that when I do that, I make that circle rotate clockwise. So the torque from F1 all by itself would tend to make this object rotate clockwise. Since we have defined counterclockwise to be the positive direction, that would be a negative torque. So now we have torque 1 equals minus. Now the R here, that's the distance from the center of rotation to the point where the force acts. That's 20 centimeters. And I'm going to convert that to meters, 0.20 meters. Then I put in the magnitude of the force, which is 5 newtons. Now here I have the sine of the angle between the force vector and the extension of the position vector. Now I did something a little sneaky in the figure here. The 30-degree angle here is not the angle between the force vector and the extension of the position vector. The angle between the force vector and the extension of the position vector is this angle in here. Now, since this is a right angle here, and this is 30 degrees, then this angle must be 60 degrees. So this angle phi associated with torque 1 would be that 60-degree angle between the force vector and the extension of the position vector. So I'm going to put in sine 60. And when you put that in your calculator, you will get minus 0.87, and then the unit of torque is Newton meters. The only other calculation I have for you here is to try and find the torque associated with force 2 over here. So the torque associated with force 2 would be plus or minus RF sine phi. So just give that a go and then rejoin the video. First, we'd like to determine whether the torque associated with force 2 is positive or negative. So I have my paper circle here again. And again, I'm going to come to the equivalent point, which would here be the point over here. And I'm going to exert a force in the direction of force 2. And you can see that when I do that, that tends to make the wheel rotate counterclockwise. We have defined counterclockwise as the positive direction. So the torque associated with force 2 would be positive. Now let's finish the calculation. Torque 2 would then be plus. Then that R here would be the distance from the center of rotation to the point where the force acts. That's 30 centimeters. But I'm going to convert that to meters. So 0.30 meters. Then the magnitude of the force, 8 newtons. And then we have sine of 80. So we get torque 2 equals 2.36 Newton meters. So now we've had our first experience calculating the torques associated with forces. In the next video, I'm going to give you a different formula that you can use to calculate torques. And this next formula is actually going to be the more useful one when we get to some example problems.